Morning students, let us discuss on continuation of our AC motors. In that induction motors we have seen previous classes. Recently we have covered induction motor, the physical constructions, working principles and few electrical parameters changes during the running conditions. Now we are going to further analysis what are the different types of losses in an induction motor. At the same time, how electrical energy is converted into mechanical energy at the shaft. During this journey, how the energy changes, losses at different places, and what are the net power available at the shaft. Okay. Before going to that, so what are the objects today we will see. Okay. So this is a topic regarding to 5th semester and AC motor subject EE 503. Subtopic is power stages in a induction motor. Today object is on completion of this period you would be able to understand about power stages in induction motors, few expressions for rotor powers and stator powers like P1, P2, PM, P out power in the terms, relation between the slip and these terms. It is a very simple. As you know that here how the power is converted, as you know that when power is given to electrical power is given to terminal box, then it will goes to the stator winding, and after that there is a development of power. The power is given to the rotor, and rotor also having some its losses. After that it will give the some net power at the shaft for loading purpose. Okay, let us see that one. Now you can see, as already you have seen in synchronous motor, how the power is transmitted from stator to rotor. Here you can see here the power input to stator. Okay, so where is the stator? You can see this is the stator. Stator has stator winding. Okay, so I can see here. Now what is happened? Let us assume this is a so this is a stator yoke. Now we have distributed R phase, Y phase, B phase, R phase, Y phase, B phase, R phase, Y phase, B phase. That means there is a distributed winding in the stator core. When 3-phase supply as a electrical energy is given, the current flows in winding, stator winding, and this winding has some resistance. The current is flowing this inductive value. Then due to the I, due to the R, there is a I square R losses takes place in winding to produce some heat energy. So whenever the current passing through this one, so it has a R and it was some leakage reactance also. When the current is flowing through the resistance, it produces some heat energy, and when the current is passing through the inductance, leakage reactance, it produces a magnetic field. Okay, so we require the magnetic field only, but at the same time, as a bonus, we are going to get it resistance, that is a heat energy also. This is in the form of wastage. Now that means whatever the power is given as an input P1 to the motor, some of the power is wasted in terms of heat energy. That means we can say this is the copper losses, because R phase, Y phase, B phase copper winding owned on stator. When current passing through the stator winding, it losses as a copper loss in the stator. Now after that, whatever the current is produce a magnetic field links in the rotor conductors. Okay, so what is the rotor now? Rotor has rotor winding also. Okay, so stator has stator, that means stator also having its some iron piece. So this is also okay. So we are also consider this value also. What is that one? The stator has winding as well as the iron core. We have the iron core also. So due to the iron core, we apply the frequency F. There is a iron losses also occurred in the stator. Okay, so whatever the power input is given P1, so the P1 is given to some copper losses of stator plus some iron losses of stator plus P that is a stator output, that let us assume stator output. These are the powers. So whatever the input is given to this one, what is the power input given? P1, we can write it root 3 VL and IL cos phi. Okay, that is power input to the motor. This power is converted into in the form of copper losses, in the form of iron losses, in the form of output energy, remaining output energy. Okay, so that is means some losses occurred here. What are the losses here? Copper loss occurred and iron loss occurred. Here copper loss is dependent upon the resistance, the iron losses depend upon the frequency. What are the iron losses? Already we have seen iron losses may be eddy current losses and hysteresis losses. Okay, so we are used laminations to reduce the eddy current losses, and we have used high silicon content material to reduce the hysteresis losses. Okay, so even then there is a small amount of the iron losses in the stator, and some copper losses also present in the stator. So that means here whatever the input power is given, electrical input power, that is a P1 is given, we can use as a P stator, that is a stator, P out, stator output. So we can say this is a plus and some copper losses, P stator copper losses plus P iron losses in stator. Okay, so this is the power. Now after that, so it flows to the rotor. Now what is happen? Once the power is coming here, that is a rotor stator output, we can say this stator output, we can say that is equal P2. Okay, so that is equal P1 is equal to some P copper losses plus P iron losses plus P2. Okay, this is the output of the stator, this is the input of the stator. These are the losses. So P1 minus P2 is equal losses. Okay, so we can that's also we can write it. So we can write it P1 total input minus P2 total output of stator is equal to losses. What are the stator losses? P copper losses plus P iron losses. Okay, so these are the losses in the stator. Now after that what will happen? So this is going to as a stator output, or we can say this is a rotor input also, rotor input. So whatever the here it comes to the is a P2 as a rotor input. So this rotor input P2 comes to the rotor after some losses. Okay, now what is happened here? So now coming to the P2, once the P2 comes here, so this is the rotor, let us assume. So rotor has its slots, so it has also slots. Okay, you can see it. So what is the rotor? This rotor has slots. Now it is a rotor bars, for example squirrel cage rotor bars, and this is the R core. That means here as the copper bars or copper winding in case of slip ring induction motor, and it is also iron core, similar to the stator. Now what is happened? Input as P2 comes here. Whatever the energy P2 comes here, and so due to the rotating magnetic field, okay, so due to the rotating magnetic field RMF, it sweeps the rotor conductors and EMF induced in the rotor conductors, and that EMF produces and the rotor current, a rotor current produces its flux, rotor flux. This flux and stator flux interaction, the torque is developed. Okay, now whatever the P2, the power input to the rotor, here we can use P2 input is equal to, so it has a copper losses. So rotor has a P copper losses, rotor copper losses, plus here also it has a iron core. But what is happened under normal condition? So rotor has a very less frequency. What is the Fr is equal to S into F. F itself 50 Hz. Stator frequency is the 50 Hz. Under standstill condition, the frequency is the 50 Hz, but at running at nearby synchronous speed, that is a 1400 RPM. Then the some slip percentage, that may be 2%, 4%. That into 50. So that value will give the very less frequency. So that frequency depend on the iron losses, that is equal eddy current losses and hysteresis losses. These are depend upon this frequency value. So this frequency, rotor frequency, very less as compared to that one. That's why we are neglecting this iron losses in the rotor. Okay, we are neglecting rotor because iron losses depend on the frequency. So at the same time, so that's why voltage also, that is equal, what is the ER, ER, that is the rotor frequency is the S into E2, that is the slip itself very low. That's why we are neglecting, for simple understanding purpose, we are neglecting the iron losses in the rotor. Then what is remaining? Then whatever the rotor will develop, that we can say is the mechanical power developed in the rotor. That means whatever the input is given to the rotor equal to copper losses to meet the copper losses, and remaining that develops the total mechanical power developed in the rotor. Okay, so then it will goes the rotor PM. So what is the input? This is the P2 is the input to the rotor, and PM is the mechanical input developed in the rotor, and P copper loss is the losses takes place here. Now this mechanical, whatever the mechanical power developed is and given to the that equal to what will happen at the, it will give the shaft will rotate, and shaft is placed on bearings. Due to this one, so that is supplied to the power, some of the power is used for the friction and windage losses. Okay, friction and windage losses, plus after that it is going to the net power, that is the P out of rotor. Okay, this is a rotor output. So whatever the mechanical energy generated in the rotor, that minus friction and windage losses, if you are subtracted, then we are going to the output of the rotor. That means here what is the rotor output? Rotor output is equal to P out. Now so that is equal to, what is the input of the rotor? P2 is the input. Okay, now minus P out is the rotor output, then that is equal losses here. What are the losses here? Constant, we can say the constant losses. What are the constant losses? This is the P copper losses, that is the changes, and at the same time mechanical losses. So P friction and windage losses, we can say the P mechanical losses. Okay, so these are the different types of losses we are going to get in induction motors. Okay, so let us see in diagram. Here you can see this is power input to the stator, that is called, let us assume V, that is equal to P1, so input power to the motor stator. Then in that what will happen? It has a copper losses, it has a copper winding, it has the iron laminations. So then some losses may be occurred here. What are the losses? That is the iron losses and copper losses. The total input minus this losses, some losses is going wasted. Now this minus the remaining, we are going to get the, so it's a rotor input here, rotor input. Okay, so this rotor input, then rotor, whatever the rotor input that we can take that is equal P2. So this is a P2 rotor input to the this one. Then rotor also having the some winding, so then we subtract the rotor copper loss, then remaining we are going to get that PM, total mechanical power developed in the rotor. Okay, so after whatever the mechanical power developed here, so here there is a bearings, you can see friction and windage losses. So subtract this friction and windage losses, we are going to get that this P out. So we can write the P out. Okay, so what are the materials used in motors? You should know. So based on this one, what are the losses may be occurred? Generally we use the winding and we use the some iron laminations. Okay, so when the current passing through the winding, there is a I square R, copper losses may be occurred, and due to the iron, due to the frequency, due to the voltage, some iron losses may be occurred. So in motor, generally in stator side and rotor side, losses may be occurred. Stator having the stator copper losses and stator iron losses, but whereas rotor also rotor copper losses and stator rotor iron losses. Okay, but rotor iron loss is very less, that's why we are neglecting these losses. Okay, so these are the losses, and after that some mechanical loss, this we can say this is the mechanical losses. So we cannot avoid these losses. These are the different type of the losses in a induction motor from starting to ending. Okay, don't confuse, you can see the another figure also elaborated. Now you can see here. So what is happened here? The motor input in the, just like we take in the P1. Okay. So this is the P1 input. Total input to the motor is the, we given the water supply is the electrical input. P1 is the. So here we are going to the, this is the P out. Now P motor input in the stator, that is in the form of electrical energy. Then due to the stator core and stator copper losses, so some losses may be reduced, losses may be subtracted from the P1. Okay. Then after that we are going to the rotor input P2. Okay. This is a rotor input, this is the, we can say the P2. This rotor input supply to the rotor copper losses, because it has also some winding copper bars. And in case of copper bars, in case of a squirrel cage induction motor, and three-phase winding in case of the wound rotor. So the current also flowing through the winding, hence we have to subtract that copper losses, Oscar losses in the rotor. After that what will happen? So total net mechanical energy developed in the rotor in the form of mechanical energy, that is going to the, or we can the gross torque. What is the torque? Torque is equal to torque into, and omega is equal to power, nothing but, okay, 25 N by 60. So this is a torque into omega is a power. So that means what the torque, net torque is developed in the rotor to rotate the rotor. And after that there is what will happen? So there is a mechanical losses also. What is the windage and friction and windage losses we are going to occur here. After that, so rotor output. So here rotor output is equal, this is equal P out, net output at the rotor shaft, and this is a P in as a electrical. This is a mechanical energy, this is the electrical energy. Okay. Now it can be simplified with this one. You can see motor input. So motor input is equal to, so it is classified that it is supplied to the rotor input and stator, this one. That means whatever the stator input is given, some of the power is used for the stator copper losses, iron losses. Now after that some of the loss is used for the rotor input. After that rotor input, it is supplied to the rotor copper losses and mechanical power developed, PM. And this PM, after that some of the losses, friction and windage losses, and after that so output will comes. So just like in the flow diagram you can see. Okay. Now here the same diagram, but in terms of P1, P2, PM, these values, because these are the very essential for while calculating the problems. Okay, that's why I am repeating these things. Okay, so motor input, what is the motor input here? P1. So here you can see the, so PW is the windage losses and iron losses and copper losses, and this is a rotor input P2 via air gap. So stator to rotor wire gap P2 will flows, and this P2 becomes the mechanical power developed, that is a PM. At the same time some of the copper losses occurred in the rotor. Okay. So after that it will goes to the some friction and windage losses, and this is the output. Okay. So because you can observe here is some, what are the parts present in the motor, all will take some power. So you can see here, this is a one bearing is provided, that is the friction and windage losses reduces, otherwise more losses may be occurred. To reduce the friction and windage losses, we have used one bearings, and to reduce the iron losses we have laminated the core materials. Okay. At the same time, so to reduce the copper losses also we are going to use a very less resistance copper conductors. Okay. Now these are the step by step losses occurred in the machine, and okay, I think you got some idea. So finally conclude that, so what is going to occur. Now once again I am So this can be same thing. So what has happened? P1. So P1 power is given to the electrical form. Electrical form P1 is given here. And what has happened? The stator copper losses, P copper losses, and at the same time iron losses. So this minus this values losses. After that we are going to the P2, that is the active power input to rotor and output to the stator. Okay. After that, so what will comes here P2, that sum of the motor copper losses, P copper losses of rotor. Here copper losses in stator, copper losses in rotor also. Here iron losses in stator, but in this also iron losses, but we are neglecting these losses. Okay. After P2 minus, so what are the P2 minus this value, so remaining value will goes, that is equal PM. So gross mechanical power developed at the shaft, we can say. So at the shaft some of the losses may be occurred further, that is equal friction and windy losses. Then we are going to get the net output available at the shaft for to take the load. Okay. So you can see this similar here. Okay. These are the losses takes place in our induction motor. Let us convert this all values in terms of slip, in terms of P1, in terms of PM, in terms of P2, and at the same time we are going to find that what is the efficiency of the motor. That depends upon what terms. Okay. So very simple. Dear students, it is a simple, this already we discussed in synchronous motor. Okay. Any motor, same, how the electrical energy is converted into the mechanical energy. We know that energy cannot be created, cannot be destroyed, but it can convert one form to the another form. Here electrical energy first is given in the form of electrical energy. Some of the energy wasted as a heat energy. Some of the energy as wasted as that is the friction and windy losses. Okay. So it converted, a remaining loss, remaining power is converted to the mechanical power at the shaft. That is the required one. Okay. Let us calculate the torques. What are the input torque? What is the output torque of the rotor? Because may require the torque. How much torque is required developed in the machine? Okay. Induction motor develops a gross torque and due to the gross rotor input, and the values are expressed in terms of our terms, related required terms. Let us see. Now you can see here an induction motor develops a gross torque Tg due to the gross rotor output. So what is the that is the torque? So we know that torque is equal to the power, whatever the input power. What is the formula? Power is equal to angular velocity omega into T, torque. So that's we can write it 2 phi n by RPS 60. We can convert it into T, torque. That is equal P. So based on this principle, so instead of power we can discuss in terms of torque only. Okay. What is the torque now? The torque can write it. So torque is equal to P by omega. Okay. This is the torque. How much torque is developed in shaft torque and how much torque is developed total torque. Okay. Let us see. Now here you can see. So Tg is the gross torque, that is called P2. What is the P2? Input by, here is a torque which is coming from the, that is equal at synchronous speed. So that can be written as a Tg. We can write it here. So that is equal Tg gross torque. So dependent of the, what is the input, total input to the rotor, that is equal P2. What is the angular velocity? W, yes, synchronous W. That is equal, we can write it P2 by, so that is equal 2 phi n s by 60. Okay, that is the input to the rotor. So that is the gross torque is developed the input to the this one. Okay, at the same time in terms of rotor output, what is the rotor output torque? That is you can write it, this is in terms of input. At the same time the TG in terms of output we can write it same. What is the value? What is the output? PM. So here the PM, what is the P2 minus this losses equal to the PM. So I want to express TG in terms of PM, that can write it. So PM by 2 phi n, only n, because rotor speed in terms of mechanical by 60. So this is the gross torque in terms of output of rotor, and this is a gross torque in terms of rotor input. Okay, so this is the first equation and second equation. So please see this, don't confuse it. Okay, now after that what will happen? So you can write the another. So all just manipulation only. Now you can see the shaft torque, that is the torque which is available at the shaft, is due to the output of the power. So what is happen here? The torque is available, the shaft torque, this is a torque shaft, it is ready to take the mechanical load, and whereas this torque is the TG, gross torque. Gross torque is developed in the rotor minus some loss torque is losses due to the friction and windage losses. Okay, then we are going to the shaft torque. Now the TG, gross torque, expressed in terms of P2 and in terms of PM. Okay, now so here you can shaft torque also we are going to express in terms of P output. What is the P out? P out is the total output in this one. Okay, P output, that is equal P output by omega, that is equal, we are going to P out into this one. Okay, so P out in the RPM here. Okay, so that is equal P out divided by 2 phi n by 16 RPS. Okay, this is the one equation. Okay, now so RPM, this is the RPS, this is the RPM, so don't confuse. Now after that we are going to the difference between the TG, that is a gross torque, and shaft torque equals the torque loss due to the friction and windage losses. Okay, so this minus this one. Okay, so you can see here. Okay, what is happened here? So once again, don't confuse students. This is a TG, this is a T shaft, this is a T gross, TG. So total torque is developed in the rotor is equal this much, but the shaft torque developed at the shaft is this much. It is ready to on road. For example, you take it one example. Okay, what is the example? Suppose you want to take the one suppose one bullet or two wheelers from the showroom. Okay, you want to take the showroom. So what is happened? Initially there is a cost of, for example, this cost may be, showroom cost may be it may be 90,000, 90k. Okay, 90k. So 90k is the showroom cost, that is the TG. At the same time, so you have to pay the some amount for the road tax and some insurance, and so what will happen? So some of the next license charges, all charges you have to add it. That is the road, on road you are going to get the nearly so 95k. Okay, so this is a on road, this is the on road amount 95k, this is a showroom price this much. What is the difference? The difference is equal 95 minus 90 is the 5k. So 5k is that is we are going to compulsory, we have to pay the insurance, road tax and something. Okay, similarly this is a friction and windage torque losses due to this mechanism. Okay, so that's why, so this is TG, total gross, this is available T shaft. Okay, available between this one, what is that? This is a very high. So because TG is a more, this is input, this is the output. Okay, so what is the in between? This is the input. The friction and wind loss, some losses you are going to take it. Okay, suppose for example take the suppose you own a one lottery you are going to own some Mangalya something place. You got the 1 lakh lottery. Okay, so he never gives the 1 lakh to you. So but actually 1 lakh you own in lottery. In that one you have to pay the some percentage, suppose 20% as tax to the government. Remaining, so 80,000 only will give you. So on hand you are going to get the 80,000 only, but you got the 1 lakh lottery. In between, middle, so 20,000 goes to the government. That is a compulsory. Similarly, here is a 1 lakh, this is the 80,000. In between 20 lakhs, 20 is going to the losses. Okay, are you understood? Now it is easy, no problem. Now let us see equations. So the difference between the TG and TSH, shaft torque and gross torque, equals the torque lost due to the friction and windage loss in the motor. Okay, in the above expression, N and NS are in RPS. Okay, revolution per second. However, if they are in RPM, so just is divided by the 60. The above expression for the motor torque we can get it. So TG here we are going to get, what is the TG? So gross torque developed in this one. Okay, so we will see here. Okay, so now, so what is that here? We are going to get the gross torque. Gross torque, that is equal to TG. So we know that P2 in terms of input, P2 is equal to omega ES and TG. Okay, gross torque. I want the gross torque in terms of P2. Then I can write it TG gross torque in terms of P2 by omega S, angular velocity. Then I can write it, that is equal P2 by, so what is the omega S? 2 phi N S by 60 value. Okay, so that is in RPS. We are going to convert it into RPM. Now then we are going to get it. So P2 into 60 divided by 2 phi N S. Now 60 by 2 phi I can write it. Okay, now I can write it 60 by 2 into 22.7 divided into NS. Okay, into P2. So I am going to get this value. Okay, I am going to value that is equal 9.55 approximately. That is equal P2 by NS. So this is the final equation. That means the torque developed in the rotor, gross torque developed in the rotor in terms of P2 by NS into 9.55. Okay, this is a formula we are going to use in calculations. What is the torque equation unit? That is the Newton meters. Okay, that is common. Suppose I want the T shaft is required in terms of output. Okay, or you can write it that in the form of PM also. Suppose a TG, this is the TG in terms of I want the PM. So simple, no, PM by N. Please remember, if in terms of P2 N is, in terms of PM is a mechanical rotor, you are going to N only into 9.55 Newton meters. Okay, so this is a gross torque developed in the rotor. Okay, suppose I want the power shaft torque. This is a showroom price. This is your lottery amount. Now I want the net on road is required. That is a T shaft. How much torque is developed at the shaft after all losses? So we know that what is the T shaft into omega is equal to, what is the, you require the P out. output power. You know the output power in terms of, you convert the shaft. Now I want the TSH is equal to P out by omega. Omega, what is the omega? 2 phi n by 60. Okay, then we are going to get it. What is the value? Same value, the 60 by 2 phi n, we are going to 9.55 P out. So this is a formula, Newton meters. That means, so T shaft in terms of output value, we are going to 9.55 into P out, we are going to get that value. Okay, so that means here what are the formulas we are going to get it? So I want the, for example, here T gross power, torque, gross torque is equal to 9.55 P2 by NS, Newton meters. Okay, this is the one equation. Or I want the PM. So TG gross torque is equal, I can write it 9.55 PM by N, M by N only. Okay, that is the difference, M Newton meters. I want the T shaft in terms of output, that is equal, you can write 9.55 P out by N only. Okay, this is a Newton meters. These are the three relations you should remember for calculation of some problems. Okay, so same thing, the power, or in terms of power, is converted to the torques only. Okay, now, so these are the equations, same equations. Now let us write for some more equations regarding to this one. Okay, topic is very simple, but we are going to try the different forms. That is equal, P is equal to I square R, P is equal to V by I, P is equal to V square by R, P is equal to, so I square R, V square by R, V into I. Similarly, we are going to write the similar. The stator output is transferred entirely inductively to the rotor circuit. So what is happened here? Here stator input P1, that is equal in the form of electrical energy. Stator output plus stator losses. What are the losses here? Iron losses and copper losses of stator. Okay, so then you have the figure also, you can see here. Figure. So here what is happened? Whatever the given, that is equal, P1 is given, and whatever the P1 is given, this is the one loss, this is the one loss. These both losses we are going to, this is the stator losses. The stator output, after that, what is the input minus this one, we are going to this one, the stator output. So stator output is transferred entirely inductively to the rotor circuit. Okay, so electrical converted to the electromagnetic, magnetic is converted to the rotor. Obviously rotor input P2, that is equal input P2, this is value, is equal stator output. This input is equal, this output is equal, this input. Okay, this input. And rotor gross output PM, that is equal, this value is equal to, so this input minus this loss is going to be this one, that is a rotor input, that is called P2, rotor copper losses, this copper losses is equal, we are going to this one. Okay, now what is here? The rotor output is converted into mechanical energy, and what are the rotor output? Is this a rotor output PM? Okay, so rotor output is the mechanical. So rotor output is converted into mechanical energy. That's why we required, and gives rise to gross torque, that is called, due to the mechanical, due to the PM, it produces a torque. The torque is gross torque. We can say this is a gross torque, that is the TG. Okay, out of this gross torque developed some loss due to the windage and friction losses. So due to from this torque, some torque is losses in this one in the form of friction and windage losses. So rotor, and the rest appear at the useful shaft torque. That's the we are going to get the TSH is the ready to take the load. This is the final torque available at the shaft. Okay. Now, here let N is the RPS be actual speed of the rotor if Tg is the Newton meter. Tg is the torque always in Newton meter. So, let us write the one equation. What is that equation? Tg into, that is the rotor gross in output in watts in PM. Okay. So, what that is in the figure already you know that. So, this is a torque into this omega is equal rotor output in watts in PM. That is called PM is equal, we can write it omega into in terms of so Tg gross power. Okay. So, this is the equation. Now, we can write it. So, there is a Tg is equal to same thing PM by 2 phi N. So, in RPS we are going to take the in the RPS. This is the first equation. Okay, already you know everything. So, this Tg is equal is given. If there were no copper losses in this rotor, then rotor output will be equal to the rotor input and the rotor will run at synchronous speed. So, actually there is no copper losses in the rotor. So, then we are going to assume that, but it is not never. Then what will happen? So, I want to write it in rotor copper losses in terms of rotor copper loss. Then this gross power I can write it in the form of Tg, the gross power is equal to the rotor input, that is a P2 by omega S, that is called. This is another equation. This is equal to, I write Tg in terms of PM, the Tg in terms of P2. Already we derived these equations previously. Okay. Now, next from the equation 1 and 2, we can write it rotor output PM and Tg. We can write it. What can we write? That is equal to whatever that one. So, we can write it here. PM is equal to, so PM is equal, we can write it Tg and omega. Okay, that is equal, we can write it the Tg into 2 phi N in RPS. Okay, this is the equation. Now, I want the rotor input, that is the P2, I can write it the Tg into 2 phi Ns only. Okay, this is another equation. This is the third equation, the fourth equation. So, same thing we are going to write in terms of Tg gross torque in terms of rotor input and rotor output only. Okay. If the rotor output in terms of N, rotor input in terms of Ns, synchronous speed, that is the only difference. Okay. You can see third and fourth equation. The difference of the rotor gross output and the rotor input equals to copper losses. Conditions is given. Now, from the equation third and fourth, so we are going to write it relation. We are going to create the relation between the what is happened, the rotor copper losses by rotor input. So, here what is happened, first we take in the equation, from the equation we are going to write it. What is that one? Here rotor input we taken, rotor input, that is equal to P2 is equal, we write written as a Tg into 2 phi N. Okay, this is the third equation we written. And same rotor copper losses we written as a, that is equal we written total input minus, that is the PM output, rotor input minus rotor output is the copper losses, that is we can write it. What is the equation we written? That is equal to, that's a Tg and into 2 phi Ns minus N. Okay. So, this is the equation. So, P2 I known, PM I known. So, here is the same thing. Okay. So, this is the fourth equation. Okay, so P2 I know, Pm I know, so P2 minus Pm we are going to write the in terms of this one, Tg, in terms of Tg. I written the P2 in terms of Tg, I written the Pm in terms of the Tg, and then subtracted input minus output. So rotor input minus rotor output is equal, we are going to write it. So Tg gross power in terms of Ns minus this one, 3. Okay, now I want to write it now 4 by 3. So what is the 4? Rotor copper losses. So rotor copper losses, okay, divided by rotor input. That is, you can write the P2. I can write it. So what is this one? Tg into 2 phi ns minus n, okay, divided by this value. You can write it this value. What is the value? Same, Tg into 2 phi into n only. That is the, you are going to get, I think this is a yes, no? So you are going to get, that is equal to here P2 in terms of ns. So here P2 means you can ns, okay. Now you are going to ns. Now Tg 2 phi, that what we are going to the ns minus n by s, that is equal to slip. Okay, so what is we are going to get here? Okay, sorry. Here what is going to, so rotor copper loss by rotor power, that is equal to here rotor peak copper losses by P2 is equal to S. That means if I want the copper losses of rotor, I can multiply whatever the rotor input into S, I am going to get the copper losses. Simple. Okay. So here I want to know the what are the copper losses in the rotor. So if I know the rotor input, that is a P2, into multiply the slip, then I am going to the P copper losses. Okay. So this is written here. So here what is happened? Rotor copper losses is equal to rotor input. So this is the we derived now. Now at the same time, so rotor cross air gap, that is this called S into P2. Rotor input, so I can write it same thing, so in the different forms. Rotor gross output is equal to rotor input minus rotor copper losses. So I am going to the rotor input minus S into rotor copper losses. So what we are going to get here, I am going to get this is equal 1 minus S into P2. Okay. So have you understood this one? Okay, I will go. So is writing the different equations. So what is the equations written? So as we know that P copper loss of rotor is equal to whatever the input of rotor into slip, you are going to get the its copper losses. Okay, that we have derived. Now rotor input and copper losses, I want the relation. Rotor output I required, that is called rotor output is equal Pm. Okay, Pm is equal, I can write it P2 minus P copper loss. Okay, so what is the P2? So I can write the P2, then I can the P copper loss in terms of this value. Okay, P2 into S. I take the P2 as a common, I can get the 1 minus S, that is equal Pm. Okay, that means this is a rotor input, this is a rotor output. Okay, then I am going to get this, that is equal, I want the mechanical power developed in the rotor is equal, total mechanical power developed in the rotor is equal to total input into 1 minus S. I am going to get this one. Okay, so I want the total copper losses in the rotor is equal P2 into S. If you know the slip, I can calculate the power copper losses. If you know the slip, I can calculate the total mechanical power developed in the rotor. Okay, so these are the shown in this slide. Okay, so this is the same thing. So dear students, don't confuse. Okay, now so I want to make the relation between the rotor input, rotor copper loss and rotor output. in terms of slip. That is my aim. Okay. So now the rotor gross output PM. So you can write it. This is already we did have this one. Okay. Now rotor gross output, that PM by rotor input, that is equal total rotor input, that is equal, what is that one? 1 minus S, that is equal. Okay. Here you can see this rotor gross output PM by rotor input P2. So 1 minus S. So what is the value? You now, just now we got it. Rotor gross, this is equal, you can write from this equation. So you are going to get it this by. Okay. So that what is the value? From this one you are going to rotor, that is called PM by P2 is equal 1 minus S. What is the 1? What is the S? Slip. Okay. You write it the Ns minus N divided by Ns. Okay. Then what is the value? Ns will come here minus Ns plus N divided by Ns. This one get cancelled. We are going to get the N by Ns. That is called this one. Okay. Now, so then you are going to that what here. So what we are going that this is PM by P2. You are going to this value. Okay. So that is equal, PM is the rotor output by P2 is the rotor input is equal, simply write the N by Ns. If you know this speed also, we are going to calculate this equation. Okay. Now rotor efficiency. What is the rotor efficiency? Now here this is a rotor efficiency, input minus output. So that is we can write this value. Okay. Also rotor copper losses by rotor gross output also we can write it this equation. Okay. Now, so now in this equation, so we are going to write it in terms of, so what is the input P2 versus P copper loss of rotor versus and PM mechanical power developed in the rotor. I can write it in the equation in the ratio of 1 is to slip is to 1 minus S. If I know this values, I can calculate anything relation. So that's why I am the created all equations. Okay. What is the P2 rotor input? Okay. You can see here. That means here this is a P2, this is a P1. Now this is a P2. Okay. It is a developed, this is a torque, this is equal T gross torque. Okay. This is a rotor. Now in this one what will happen? So this P2 TG, I can write it, this is a TG, all things I can write. And here what will happen? There is a copper loss, P copper loss occurred in the rotor. Then we can write it in terms of power. This is equal PM, total mechanical power developed, this one. So P1 given to the stator, that is transferred in the form of magnetic field, that is the input to the P2, sum of given to the P copper losses, and remaining developed as a PM. Okay. So now this is equal, what will happen? P2 is equal to P copper losses plus PM. I want the relation between these three. So what can I do? I can write it, that is equal P2 and P copper and PM. I can write it 1 is to S is to 1 minus S. I can write it this equation. That means this is equal P. So I want the copper losses. Suppose if you know the P2, if you know the P2, I want the P copper losses of rotor. I can simply P2 into S, I will get the copper loss. Suppose I want the PM I required, simply, so you can write it, that is called P2 minus P copper loss, you can get, or otherwise you can simply the P2 into 1 minus S, I can get it, simple equation. So that's why dear students, remember the relation, this relation. Okay, then you are going to calculate any problems. So now you have some idea what is the significant role of slip in induction motor. If you know the slip, you are going to find that what is the torque is developed in the rotor, what is the copper losses in the rotor, what is the rotor input, and everything we are going to calculate. Okay, so these are the some relations in induction motors. If some power P2 is delivered to the rotor, then a part SP2 is lost in the rotor itself. So losses, already we have seen these all things. Okay, so hence it is advantage to run the motor with a small slip as possible. So here our aim is to run the slip should be the very less. Initially the slip is equal to 1, and at under running condition the slip should be the minimum. Okay, so that's why we are going to run it slip as possible as small value. Otherwise what will happen? So I want the P copper loss. P copper loss is equal slip into P2. So if slip value is called 4% of, for example, 10, what is the 4%? That means what will happen? 4% means 100. So P2 is equal 100. Then 4% by 100. We are going to the only 4. Copper loss of 4 watts. Suppose slip is equal to 2. Then we are going to 2 watts only. So we require these are the loss. As possible as required, I require the less values required. Hence, so to remember that, so it is advantageous to run the motor with a small slip S value as possible as. Okay, so these are the some regarding to the terms. And another one important term generally known that. So what is the synchronous watt? What is the synchronous watt? That means you can see here. Sometimes we can write the synchronous watt. What is the synchronous? Synchronous watt. The synchronous watt is nothing but P2. Please remember, in terms of synchronous wattage. It is a new unit of torque defined as the torque which develops a power of 1 watts at the synchronous speed of the motor is known as a synchronous watt. So I can explain once again. The torque which develops a power of 1 watt, power of 1 watt at synchronous speed is known as a synchronous watt. Okay, it is a new unit of torque and defined as torque which develops a power of 1 watts at the speed of synchronous speed of the motor. Okay, the synchronous watt torque is equal to, you can write it, rotor input. Rotor input, what is the P2? Okay, rotor input divided by 2 omega s, that is we can write the omega s. That means you are going to write it, this is equal P2 and this is equal 2 phi n ns by 60 at synchronous speed. Now that we are going to get that this is known as the synchronous watt. Okay, don't confuse. Synchronous watt of an induction motor equals the power transferred across the air gap to the rotor. So whatever the P1 is given and some losses, the P copper losses of the stator removed from this one, remaining what are the P2 comes, the P2 is nothing but synchronous watt. Synchronous wattage of an induction motor equals the power transferred across the air gap to the rotor to develop the mechanical energy. Okay, so this is synchronous watt. Now we know the all relations among this one. What is the T shaft, what is the teeth, everything we know. Now let us find that what is the efficiency of this one. The efficiency of induction motor. Efficiency of induction motor. We know the input, we know the output. So, we know the percentage of efficiency is equal to the input by output into 100%. Okay. So, what is the input here? We know the rotor efficiency. For example, you take the total. Here total input is input by output. This is the efficiency, sorry, some blunder. So, what is the efficiency? Percentage of efficiency is equal to output by input, na? Just output by input, okay, into 100. What is the output here? Output is equal P out. What is the input? That is called P1, okay, into 100. So, this is the percentage of efficiency of induction motor. And further, we are going to calculate rotor efficiency. What is the rotor efficiency? Let us rotor efficiency. So, what is the rotor efficiency? That means, what is the rotor output? Rotor output by rotor input. Rotor input. So, here what is the rotor output? So, we can write it rotor output is equal to P out. Okay. What is the rotor input? That is called P2. Okay. P out by P2. So, that we are going to write it. What is the P out, the rotor output? So, same thing I can write it in terms of P2, power in terms of P2 also. P out is equal to, we can write it the P rotor output. Okay. That is, I can write it rotor input minus, what are the losses? We are taking the constant losses. That is the P copper losses of rotor. Okay. Copper losses. Okay. So, here I am going to the this one divided by P2. So, here what is the mechanical and windage losses? We are taking the some for a moment I am neglecting that one. So, here P2 minus P copper losses, I am going to the P out. Okay. So, here what we are going to get? P out is equal, that is equal PM now. So, P out is a PM, that is equal nearly P out we taken. So, friction and windage losses we taken some very less, we are taking the neglect here. So, here I am going to the P2 minus P2. So, what is the value you are going to get? P2 by P2, that is called 1 minus P copper losses, okay, copper by P2. Okay. So, what is the value I am going to write it? So, I know that the P copper losses is equal to S into P2, derive this one. Now, I want the P copper loss by P2. So, I can write it. So, this can be, I write it P copper loss divided by P2. I can write it, this is called slip from, you can see. Okay. Now, I substitute this value in this one. So, what is the value? 1 minus S, I can write it. Okay. I can write the S. So, now what you can write it? 1 minus S. S means Ns minus N divided by Ns. Okay. So, I want the rotor efficiency in terms of speed. So, that purpose Ns minus Ns plus N divided by Ns. Okay. So, this and this get cancelled, then we are going to N by Ns. So, here efficiency of the rotor efficiency. What is the rotor efficiency? We write it rotor output by P out. We can write the P out by P2. That is equal to rotor efficiency. Rotor efficiency. So, rotor efficiency is equal to N by N2. I can write it. Okay. That means rotor P out, if you know the P out, the P2 input is equal to N by Ns. So, this is a relation for this one. Okay. So, if you know the rotor speed, if you know the synchronous speed, I can easily calculate the So, P out and P2. So, these are the different relations of induction motors. Okay, all are similar, just deriving the relations. In problems, you will give the N, you will give the NS, you will give the P2. You are going to calculate the what is the P out. Sometimes just exchange the terms. So, you can enjoy these formulas while doing the problems. Okay, dear students, don't confuse, just to practice it, you may get the commanding on these things. Okay, now let us summarize what we have seen in this class. So, to understand about the power stages in induction motors and expressions for rotor relations. Okay, so main relation you should remember that is equal to P2 is to P copper losses is to Pm. Okay, mechanical output development, that is equal to, you are going to get it, 1 is to slip is to 1 minus slip. So, with this one, if you know this one, we can do the everything, or at the same time also we calculate the efficiency of the rotor. So, P out by P in, that is called P2. We can write it the P2, we can write the P2. Also, I can write it in terms of, that is called N by Ns. Okay. So, from this one, so if you know that this, we are going to solve the simple problems. At the same time, so we have also seen synchronous watt. What is a synchronous watt? As a torque which develops a power of 1 watt at the speed of synchronous of a motor. If the motor is running at a synchronous speed, at that condition the torque which is developed the 1 watt, that power is known as the synchronous watt, that nothing but P2. Okay. So, dear students, please go through this matter in your textbook, and if you have any doubts, clarify in the next class. Okay. Thank you for listening.